Thank you very much, and thank you very much to the organizers. I'm always happy to be back in Princeton. And so today I would like to speak about birational boundedness of Calabi-Yau pairs, or like just Calabi-Yaus. And so first of all, this is joint work with Roberto. Roberto Svaldi, and so it's gonna be over C, everything I say. So you can think about these things in positive characteristics, but so there are still some missing things. Okay, so first of all, let me start with motivations, why I'm studying these kind of questions. And so there are a lot of motivation to study boundedness properties of Calabi-Yaus. So the first one, it's a problem I've always been interested in, is the effective Ithaka vibration. And so this is a very classical problem. Basically, you look at varieties with non-negative codiral dimension, and you look at the linear system defined by the canonical class. And so you would like to have an effective number such that power of the canonical class gives the Ithaka vibration. So the setting is that, like, let's take X a smooth projective variety. With non-negative codiral dimension, so let's say codiral dimension of X greater than or equal than 0. And then you ask yourself, so the problem is, say question, is there, so let's fix the dimension. So the dimension of X is n. So in my talk, the dimension of X is always going to be n. So is there, let's say a number, a positive number, let's call it m sub n. This number should depend only on the dimension, such that let's say mkx gives the Ithaka vibration of X. And this is for any m, let's say, divisible by mn. Okay? So you want the divisibility because otherwise it wouldn't be true. Okay, and so we know a lot of partial results to this problem. For example, if we just work with varieties with, say, of general type, so when the canonical class is big, then we know the existence of such a number. And we've been a lot of partial results for the case of non-general type varieties, but now finally, like Birkar and Zheng, so they reduce the problem to just a boundedness on the fibers. So let me, like, just in words, like the usual approach to this problem is to study boundedness on the base of the Ithaka vibration and then boundedness on the fibers. So Birkar and Zheng, they proved boundedness on the basis, and so now the only thing left is to understand the boundedness of the fibers of the Ithaka vibration. And so if you look at the Ithaka vibration, when I restrict the canonical class to the fibers, I get something trivial. So it means that the fibers of the Ithaka vibration are somehow Calabi-Yaus, so they have trivial canonical class. And so let me write, like, kind of sloppily, so reduce the problem. So I want to say boundedness, let's put up some quotations, of the fibers.
But they reduce to specific boundedness, like B1 and something.
Yeah, so I'm going to write it exact. So there are basically two things you need to understand. And so one is a topological boundedness result. There should be finally many topological types of, well, let's say, Calabi-Yau. So at least I would like to have a uniform bound on the Betti numbers of the fibers. And the other, so there is like one topological problem. And so one boundedness, like let's say boundedness of Betti numbers. So I'm being very sloppy here, so I don't want us to go into much details. So, but there is a boundedness statement, like very precise boundedness statement, on one Betti number of a variety, which is not really the fiber, but it's a cover of a fiber. Okay. So boundedness Betti numbers of the fibers. So in some sense, it's not very precise. And then the other thing is that, as I was saying, so the canonical class is trivial on the fiber, and so I would like to have an effective non-vanishing result for the canonical class of the fiber. And so the other result I'm more interested in is this. Actually, let's write it down. So it would be exactly this question in the case where the canonical, sorry, when the Goddard dimension is 0. So when the Goddard dimension is 0, I don't, like the Itaka vibration, it just goes into a point. So it's just saying that for some m, then mkx has a section. Okay? And so this is the first, and so the second one would be like, so there exists this mi, so mn, when Goddard dimension is 0, such that now I'm just looking at non-vanishing. Let's do this. Okay, it's not empty. Okay, so I'm more interested in, for the purpose of this talk, in the second part. And so we have some partial results for this problem. So we basically know it up to dimension 3. Okay? Dimension 3, we know that there is an effective bound of this form. We know the number. So basically, it's also kind of sharp. So we know everything, but we don't know anything in a higher dimension. So if the dimension of the variety is greater than 3. And of course, like especially in this conference, we like pairs. So I can ask the same thing for pairs. Okay, for a log canonical pair, like say kx plus delta now is as positive Goddard dimension. You can ask the same thing. Birkas-Young works in exactly the same way. And so this will still reduce to this kind of problems. Okay, so let me state the problem again, so because something I would like to know the answer. So now I'm looking at, like, let's take KLT pairs. I have something KLT. So maybe let's be. So I fix n and a set I, which is DCC. So DCC means that it satisfies the descending chain condition. So no decreasing sequences. And so then I would like to have, then there exists, again, this mn sub I. Now is this number is going to depend only on the dimension and the set, such that say if the kx plus delta, so let's do only the Calabi-Yau case, so I want this to be numerically trivial. If this is numerically trivial, then this m times kx plus delta, this is actually trivial, again for m divisible. Okay? So it would be something similar, but now I'm looking at pairs with trivial canonical class. And so if you want to do Goddard dimension 0, then basically the same, you can run the minimal model. It should follow from this one. And so again, here we know even less. So we don't know this problem in dimension 3. Yes, sorry. Yeah. Okay, so I'm looking at the set of KLT pairs with dimension n of course, the coefficients of delta in I, so being a little bit quick there. Okay, but yeah. Okay, so so this is one set of motivations for boundedness of Calabi-Yau. So it would be like a very weak boundedness of Calabi-Yau pair. But there is also another like set of problems that I'm interested in, and I would like to spend like 5 minutes talking about Calabi-Yau with analytic vibration. Okay, so now let's do a very easy setting. Again, X smooth. Say it again.
You don't need to require the MNI k extracted that also a big trivial.
That's for all m.
For all m divided by that guy.
Okay, sure.
Yeah.
I missed that.
Yeah. Sorry, yeah, I was a little bit too quick there, maybe. Yeah, but definitely. I'm also like including, so that there is this non-trivial statement. This is actually numerically, this is actually linearly equivalent to 0, which is not trivial. So something you proved probably. Okay. Okay, so I have an X smooth projective Calabi-Yau. So now by Calabi-Yau, I really mean like a honest Calabi-Yau. So Kx linearly equivalent to 0, and then let's say that I need some condition on the HIs, or maybe, so either H1 of X or X is 0, or they're simply connected, or even the algebraic fundamental group to be trivial. Okay, so I need some condition on the. And then I'm looking at elliptic vibrations. And so let's say with an elliptic vibration. Vibration pi from X to Y. Okay? And so I would like to study a little more this kind of varieties. And so it all started because actually Janos asked me to prove that if the Calabi-Yau has dimension 4, then like what we expect is that Calabi-Yau fourfolds with analytic vibration, they should be like maybe birationally bounded. So they should be only up to a birational map, finally many families of Calabi-Yau fourfolds with analytic vibration. Okay? And this should imply some cool statement, something like this. There are finally many universes in F theory. And so that's why I got excited. But anyway, so let's see what happened in this case. So let's assume the dimension of X is 3, which is the case we know more things. And so I want to explain this case a little bit, because it is gonna maybe tells you like the idea that you'll see later in a slightly easier setting. And so one of the tools we use to study elliptic vibration is the second Chern class. And so there's this famous theorem Miyaoka that says that the second Chern class is non-negative on the NF cone. So basically if I take C2x times something, say H, this is non-negative if H is ample. Sorry, if H is an F. Okay. And so we're going to use the second Chern class to study elliptic vibrations. And so the idea is like, let's assume something more. So I know that the second Chern class is positive, is non-negative, so let's assume that it's positive, like strictly positive on the F cone. Again on F cone. Okay. Then if I have an elliptic vibration, what I can do is like, so this elliptic vibration, I take a very ample divisor here, C, very ample. Okay, so take a very ample class, which is going to be a curve. Then I can pull it back. So let's take S to be the counter image of my very ample divisor, and so I have a surface which is an elliptic fibration over C. So you can show that this is so this is a minimal surface. And if you do a little computation with the usual exact sequences, you can compute C2 dot S. Okay, so if you want to compute this thing, so use the Euler exact sequence, so you restrict the tangent bundle, and so you can show that this is C2 of S. Okay, and then another formula, so this is elliptic fiber, canonical class is trivial, so this is 12, the Euler characteristic. Okay, so you can write this 12 times 1 plus H2. Yeah, I'm using the H1 of the Calabi-Yau is 0. And then now if you do like some other manipulation, which I'm gonna skip, this is, so again, use the exact sequence S into X. You can bound this thing by H naught of basically the global sections of C in Y. So it's 1 plus H naught of Y of S, sorry, of Y C. Okay? Okay, so this is nothing too fancy. But so remember that this this divisor S is exactly the divisor giving me the elliptic fibration. So that's why I'm trying to understand these kind of configurations. And so now if I have that assumption that C2 is positive, let's see. Let's draw a picture of the F cone. So suppose you have your F cone. Okay, so I know that like C2 it defines an hyperplane. So this is C2 of X equals 0. Okay, so this is the space of divisors such as C2 X times the divisor is 0. And then I'm assuming that this is strictly positive. And so C2.S is going to be something like some translation of my C2. Like C equals to N, okay? And so the picture says that if I want to look at integral classes here, since this is like a bounded thing, the integral classes are like a lattice, I have finally many in here, okay? So if I can bound this number uniformly, then I would have that there are only finally many elliptic fibrations with C2 positive. Okay? And so we can bound.
The boundary points are
should be, yeah, so this, yeah. Same better. Yeah, but that's a slide, yeah. Okay, because I'm just looking at F divisors. Okay? And so basically I'm doing this thing because I want to tell you that this, for example, understanding elliptic fibrations of this type, it boils down to understanding if the bases are bounded. Of course, like bounded here in this case, it means that I have a very ample class with bounded degree. Okay? Okay. And so now this is true. And so this is Alexeyev result. Alexeyev's theorem implies that basis of the elliptic fibrations of these are bounded. Okay, so in this case, like you actually, the set of all possible bases they are obtained this way are bounded. Okay, and then this is uniformly bounded, and so this will be less than some m that does not depend on my choice of x and y. Okay? Okay, so let's see like how, let's see maybe better the statement of the Alexeyev result. And so the idea is that if I have such a fibration, then I would like to use something like a generalization of Kodairas bundle formula and show that Y itself is a Calabi-Yau pair now. Even if this guy was a honest Calabi-Yau, this is now a Calabi-Yau pair. And this is exactly, it's basically Kodairas bundle formula. Okay, so we have this canonical bundle formula. This implies that there exists a divisor, let's call it delta Y effective on Y, such that this Y delta Y is KLT, and KY plus delta Y is trivial. Okay? And also, since we are in this particular case, I also know that Y is a rational. Y is rational. Okay. So yeah. So canonical bundle formula implies that Kx plus this Y, is a log Calabi-Yau, and then Alexeyev showed that if you are in this setting, when Y is rational as well, then they form a bounded family.
You don't need a birational change of Y here?
No, we don't need a birational change. Yeah. Okay? And so let me now state Alexeyev result wise again. So if I have a so Y is a surface in our case, so if I have a log Calabi-Yau surface with Y rational, this is KLT, is actually epsilon KLT, so I can control much better the singularities, then Alexeyev says that they are bounded. So in particular, there is a uniform bound for this H0. And then, this is a theorem of Guizot and Peternel, which I forgot to say. So Guizot and Peternel, they notice that Alexeyev result implies that there are only finally many elliptic fibrations with C2 positive on a Calabi-Yau threefold. Okay. And so the goal of this seminar would be try to understand a similar boundedness statement to the one of Alexeyev. Okay. Because I would like to understand, for example, if the bases of any elliptic fiber Calabi-Yau are still bounded or not. Okay, so there are still few problems that we need to take care. So let's go back to the elliptic. So again, to the elliptic Calabi-Yaus. Okay, so we have this pi from X to Y. And so there are a few cases that I need to avoid. So basically the trivial cases. So if I take like a Calabi-Yau across an elliptic curve, then this would be an elliptic fibration. And like bounding Y's would be bounding the actual Calabi-Yaus. And so this seems to be a very hard problem, which I want to avoid. And so, or like you can say that I want to avoid trivial elliptic fibrations. So I want to avoid the case where X is a product. Okay, so in the case of a Calabi-Yau, so we have a nice result of Collar and Larsen that says that if I have a Calabi-Yau, so say X Calabi-Yau, and now I have F from X to Z, dominant map. This is a rational dominant map. Okay, so if Z is not uniruled, then, so out to a final cover, X is a product, okay? So up to an étal cover, say X is a product. Okay. So if Z is not uniruled, means that that is basically a Calabi-Yau itself. Okay, and so this implies that if I have this kind of elliptic Calabi-Yaus and I want to avoid the one without product, it means that Y is, so I'm going to show you is a rational connected variety. Here it was just rational. In general, for higher dimensional, we consider only rationally connected. Because you can always run the MRC vibration. If it's not rationally connected, the basis would be uniruled. You can apply Collas-Larsen theorem, and then it would be up to an Étale-Cover, a product. Okay.
So maybe it's only a quasi-Étale-Cover. I mean.
In dimension one, in codimension one.
Yes.
Yeah. To an Étale-Cover in. Okay. So the main case would be where Y is rationally connected. Okay, and so that's the standard reduction that we do. Big. So I have this very vague definition of Calabi-Yaus. Like, of course, you can take like a K3 cross a P1 that the cross are an elliptic curve, then it wouldn't be bounded. So you need to impose some condition. And so for elliptic vibration, it seems that this imposing the Y is a rationally connected seems the nice condition. Okay. Okay, so let's see. So unfortunately, I would like to have a similar theorem for Calabi-Yau's pair. Calabi-Yau's pairs. So let's see. So now let's move on to pairs. So I have X delta. So it's a Calabi-Yau pair. If X plus delta is trivial and X delta is KLT. Okay, and so this is my setting. I want to understand boundedness of this kind of pairs, and so again the motivation is they should be basis for elliptic vibrations. So now I need to translate this condition to my pair setting. And so it would be nice to have something like Collas-Larsen theorem. So if I have a Calabi-Yau pair with a dominant map which is not uniruled, then it splits like it's a product. But I don't think I can prove something like that. But so I can prove something very close. And so let's start. So I'm going to first tell you like a structure theorem for this kind of pairs, and then I'll tell you the main result that would imply some boundedness properties of these things. Okay, so we have a structure theorem that implies something like Collas-Larsen for pair. Okay, so this is, let's call it theorem A. Okay, so we have a Calabi-Yau pair. Okay, so then there exists a birational map. So a birational contraction. To let's write X. This is birational to X prime, and X prime satisfies some such that. So X prime satisfy like a weird condition. Basically, it's a tower of Mori fiber spaces. So I have X prime, let's call it X0, X1 up to Xn. And these maps F0, Fn minus 1. They are all Mori fiber spaces. So Fi is a Mori fiber space.
For what bounded?
for kx. Thank you. It's a okay, and the last one is a Calabi-Yau, so the canonical class is trivial. So if I end, okay, and so the point is that so they are all KLT because I start with something KLT, so they are all KLT. So here maybe I can have a boundary too. Okay, so this would be the push. Okay, so we have this structure theorem that, like, if you start with a Calabi-Yau pair, it's birational to this weird modified space, where we basically encapsulate all this negativity in these steps, and then the last one, it's either, so it's something like a Calabi-Yau, a KLT Calabi-Yau, of course can be also a point. Okay, so that's the main issue. So that can be either this thing or it's a point. Which we finish with the last guy, which is a Fano. It's a Fano variety. Okay. So maybe I'll tell you like 5 minutes how the proof of this thing goes. So first of all, you start with this Calabi-Yau. So if delta is 0, then there is nothing to prove, right? It's already something of this sort. So if delta is not 0, then I know that the canonical class is not pseudo-effective. So there are a lot of details. Like, of course, you need to go to a small Q factorization of the variety. But anyway, you can run a KX minimal model, and you end up with a modified space. So actually, let me write a few words on this. So the idea is you run a KX minimal model. Okay, and so you have this map x prime, let's write y prime, over z prime, and you end up with a Mori fiber space. Okay? And then you can push forward the boundary, and so I also have a delta y prime here. Okay, and then you can prove that this is also a Calabi-Yau pair. Okay, so now you apply again canonical boundary formula. You also have a boundary here. So now you have to be a little bit careful, but you can prove that there is, so basically Ambrov proved that there is a boundary, delta z prime, such that this is again a KLT Calabi-Yau. Okay, and so if delta is 0, then I'm basically done. If delta z is not 0, then I can run again a KZ minimal model. Okay, and I end up with something else. I ran out of letters. Okay. So by now you have this weird chain of minimal models. And so what I want to do is, suppose that this is the first step of the minimal model here. So suppose there is only one step. I would like to complete the square and get a modified space here. Okay, so that I would have this kind of chain altogether, modified spaces. And so you can do these things. And so these are relative, like a two-ray game. So if you know the two-ray game is whenever you have something of Picard rank 2, so this contraction is given by one of the boundaries of the, say, of the NF cone. Then if the relative Picard number is 2, then you have another boundary. You have another ray, and so you show that that ray is also semi-ample, and it gives you this other contraction. Okay? So this is a pretty famous argument. It's called this, like, two-ray game. Okay? So I learned this like in the flipping abundance. Okay? So I will not tell you all the details, but the idea is that you run this two-ray game on all of these minimal models, and you end up with something of that sort. Okay. And so now once you have the structure theorem, the case I want to avoid are exactly these cases. Okay, so now if this is, there is a problem. So suppose that xn has canonical singularities, then this implies that xn is not uniruled. Okay, so we'll be in the setting of Collar-Larsen theorem. And then Ambrose shows that if I have something of this sort, then my variety is again a product. Okay, and so this would imply, this implies Collar-Larsen theorem in the case of a Calabi-Yau pair, but I need to have this birational map. Okay, because I run the minimal model first. Okay. And so this implies something like Collar-Larsen. So this is a corollary. Here I really need Ambrose results, and so if I end up in this situation where where xn is not a point, then x is birational to say x prime, which is again a product.
But you said canonical singularities.
No, yeah.
So you have some.
I don't need canonical singularities for the splitting.
Oh, okay.
So I need canonical. So if xn is canonical and numerical class 0, then it means that it's not uniruled, and then this would be Collar-Larsen's theorem.
Okay, I see.
Okay. So if can is trivial, then x is birational to this x cross z. Again, up to an étale cover. In codimension 1. Okay? And so I want to avoid these, I want to avoid Calabi-Yaus which are a product, and so I want to avoid this situation. Okay? And so there is a little annoying thing is that if xn does not have canonical singularities, then it's not uniruled. So for example, you have surfaces such that kx is 0 and they are rational. Okay, because they have KLT singularities. And so their case, unfortunately, is not clear. So they may be bounded. Say that again?
You can't use the canonical singularity.
No, I don't think so. Yeah, you take a cover.
After doing after the terminalization, then so.
It's not conduction.
It's not contract.
Not conduction.
So this is the.
Yeah, but those are all KLT.
Yeah, they are all here.
Yeah. No, I don't think so.
You can now again maybe then so again you can.
I'm not completely sure. Maybe we can talk about it, but. Yeah. Okay. And so, anyway. So, but let's give them a name. I don't know. So I want to call these Calabi-Yau pairs such that this xn is not 0, like not of a product type. So I want to give them a name. So if we are in this situation, meaning this one, okay. X delta is a product type. Okay. So again, it's birational to a quotient of a product. So it's not really a product, but it's not far from being a product. And so my dream would be like to say that if I have a Calabi-Yau not a product type, then they are log birationally bounded. So one remark is that So this thing is a little bit technical, but I really need this kind of condition, because if I take K3 cross a P1, then I take the boundary that makes a P1 a Calabi-Yau, then this is a log Calabi-Yau pair. So KLT is a Calabi-Yau pair, my definition. And they are clearly not bounded, right? They're not birationally bounded. And so I need to avoid the DR products. Okay, so I really need this conditional product type. So the only slightly thing I'm not completely sure if I really need this extremal case where this is KLT and trivial canonical class. So they may be bounded, but I'm not completely sure.
Are you assuming something about the boundary? Like the coefficient of the boundary? Or?
Not yet,
Okay.
but yeah. Okay?
If you assume PCC, then they will bound it, right? It's KP times P1.
No.
Okay.
No, please.
I'm just taking the boundary on P1.
Okay.
So just take 3 points or like 4 points, whatever, with like a half. Right? Yeah. So these are not bounded if you assume this is C or like fineness of the coefficient. Okay. All right. So I can state the main theorem, which is like now I'm gonna fix the coefficients. Let's write it here. Okay, so fix n. Unfortunately, I have this condition on the dimension, so I'm going to explain why. So fix n less than 4, and again at this is C set. Like you can assume finite set, let's just do finite. It's the same. So then the set of Calabi-Yau's pair of Calabi-Yau not of product type. Again, so this means that dimension is less than 4 and coefficients are in I. Then a product is log birationally bounded. Okay, so log birationally bounded means, so birationally bounded means that it's birational to a bounded family, and this log is a technical like condition that you actually control the components of the boundary divisor. So if I have time, I'm going to tell you why it is log birationally bounded, but we can prove that it's birationally bounded. So it's birational to a bounded family. Okay, this would be the easy part, and so the easier part. Okay. And so I have some time. So I want to tell you some of the ideas involved in the proof and why we need that condition on the dimension of the variety. Okay. So let me go there. So again, let's try to do.
Is that always exclude the canonical divisor itself being trivial? Is there always a boundary on this?
Yeah, there is always like yeah.
Okay. The boundary's not 0, so.
Oh, yeah. So let's write x delta. Yeah, somehow that like I always consider to be a product. Anyway, yeah.
Yeah, but does it follow from not being a product type?
Not really. So it's like 3. No. So you're right. So let's assume it's not 0.
I mean, do you count a product with itself?
Yeah, so it is a product, but it sounds a little bit weird, right? Yeah. So no, that's one. Yeah, but it's considered to be right. Okay, so let's see the ideas. So unfortunately, it's a little bit technical proof, but so I'll try to. So I feel this is the only conference where I can tell you the proof. So I'll try. Okay, so. Again, the idea is I have this structure theorem. So since I'm doing birationally boundedness, I can just try to understand if these Calabi-Yaus with a modified vibration are bounded. Okay, so the structure theorem reduce the problem to a modified by space, which is also a Calabi-Yau. Okay, so we need to study boundedness. So we need boundedness of Calabi-Yau modified spaces, modified by spaces, sorry. Okay, so now the setting is I have this X with this, let's say, P over Y, and this I have a KLT Calabi-Yau, so this is KLT. Kx plus delta is trivial, and P is a modified by space. Okay? And so the structure theorem says that if I know boundedness for this kind of varieties, then I'm done. Okay, and so the idea to prove boundedness of in general fibration is you like to have an ample divisor here. So how do you find an ample divisor? Is take an ample divisor here, I put it back, I add some of the fibers, that's ample. So then I would like to control that divisor. Okay, so as a preliminary step, let's assume that these guys are bounded. Now suppose that H is a very ample divisor. On Y with, say, bounded degree. So H, the dimension of Y is less than some number T. Okay? And so I will tell you then why this is, we can assume this thing. So now let's see, suppose we have a modified by space, bases are bounded. I would like to show that they are bounded. So yeah, I really need to use KLT. I need to use that this is a Calabi-Yau, right? Otherwise, like, Hirzebruch surfaces. They have bounded base, but they're not bounded. Okay, so you need to use Calabi-Yau. Okay, so let's do that. And so how do I find a divisor? So I know that when I restrict Kx to the fibers is the negative ample, so if I, in particular, since P is a modified by space, if I take delta, say, little delta delta plus the pullback of H, this is ample. Okay? And this, I'm assuming that I'm using here that this is a modified by space, and this is for any deltas. Say, I'm going to use for very small deltas. Okay, and so the idea is that now I want to use Kx plus, say, 1 plus so this guy is ample because it is the same as this one, is ample as well. Okay, and so if I want to prove boundedness, I need to show that the degree of this divisor is bounded, is uniformly bounded. Okay, so there are a lot of results that from the famous paper of Egon, McCarran, and Shu that I'm going to use. So I'm going to say just in words. So if I can control the discrepancy of these divisors and the coefficients, which I can, and then I can control the degree of this divisor, I can prove that they are bounded. And so this is a big theorem that Egon, McCarran, and Shu proved. So, but the main point is that I don't need the coefficient of this guy to be in a DCC. Okay? I just need to control the discrepancies. And so this one is semi-ample. And I already have that this is KLT, like when I use delta. And so I can move delta as close as 1 as I want, and this pair would stay KLT. So now there is a very subtle point. I'm not using delta uniformly. Delta is going to 0 probably. Okay. And so these are very subtle point that, like, there is this problem that if I have a Calabi-Yau, then I can add a little bit of the boundary and still be KLT, like uniformly, which I don't know how to prove it. But here you don't need that thing. Anyway, so there are a lot of bunch of like subtle stuff, and the point is that it reduces to bounding the volume of the boundary. So reduces to a uniform bound say on the volume, let's write the volume of delta plus the pullback of H. Maybe let's put a little delta here. So the volume is the asymptotic growth of the global section. So if this guy is ample, it's just the top self-intersection. So I want to use volume because I need some properties of the volume. So I would like to show that there is a uniform bound for this thing, or like this. Depends only on the dimension and the set of coefficients. Okay. And so this reduction is again basically Hegel-McHenron issue with some tricks. Okay, so I want to tell you how to bound the volume for this thing. Okay. So I know that yeah.
For the Princeton surfaces, you mentioned that, and the idea there is that if you try to make each one of those into log Calabi-Yau, you have to have more and more of the negative section, and so it doesn't satisfy DCC anymore.
Yeah, exactly. So if you bound the coefficient, then you're going to bound exactly the top self-intersection of the section. Yeah. Okay, so the way we bound this thing is like, you can do like kind of algebraic manipulation, or you can use something like the differentiability of the volume. So you like say differentiability of the volume implies that this volume is less. So I'm taking the derivative with respect, say, this direction. This is going to be less than the volume of delta plus, say, n, the restricted volume of this thing to F upper star H. Like, let's not use the restricted volume. You can just use the volume of the restriction in this case. Okay, again restricted to this thing. Okay. There is a plus missing. Sorry. Okay. And so this follows from the differentiability, or like you can do it like maybe by hand too. So it's not hard. And so now I need to bound uniformly these two things. So the volume of the boundary of a Calabi-Yau pair is bounded by Hegel-McHenron issue. And so this part is okay. And so I need to bound this part. Okay. Okay, so now the good thing is that I'm working on F upper star H, and this is a lower dimensional variety. Okay, but now the problem is that it's not going to be a log Calabi-Yau anymore. Okay, and so now you do this computation, so and the problem reduces to this new problem now, which instead of having a Calabi-Yau, so let me write, so new problem, is that we have a new setting that now, this is KLT, I still have a modified fiber space. But now Kx plus delta is numerically trivial to the pullback, maybe I used F before, of H. Okay? So I replace F star of H to be X. So now I'm in this new setting. Okay? And so this unfortunately is not anymore a Calabi-Yau. So if it were to be a Calabi-Yau, then I could use again Hegon-McKernan-Schur and bound the volume of the boundary, but this is not the case anymore. Okay, so I'm going to tell you the trick because I kind of like it. So suppose you are in that setting. Now I want to bound the volume of delta. Okay. And so the naive idea would be so the naive idea would be like I can do kx plus delta minus this f upper star h. This is numerically trivial. Okay. Then if this thing were to be effective and KLT, I would use Hegon-McKernan-Schur, right? So, but I don't know if I can prove. Like I don't know I can prove that. Okay. So there is no. At least I have no idea how to make this into a KLT boundary. Okay. So that's the naive idea. Let's see the actual idea. So now again, suppose I can suppose delta big, of course, since I'm trying to bound its volume. So the volume is 0, then I'm more than happy. So I can assume that this is big. And the volume, and with very large volume. Okay, very large as a meaning, which I don't have time to see. But anyway, so I can assume that the volume is arbitrarily large since I'm trying to uniformly bound the volume of delta. And so if the volume of delta is arbitrarily large, then delta minus S upper star h, this is effective. So meaning it's still a big divisor. Okay? Because the volume is arbitrarily large, you use one of these exact sequences. And so this is as big, like I'm always using that delta there, like, which I forgot. So let's put a little delta here. This is still big. So in particular, there is an effective divisor, which is Q linearly equivalent to this thing. But I have no idea that if this pair is KLT, and it may be false. Okay? Okay, so I need to use something slightly different. And so the thing is that when I restrict E delta to the fibers, I still get Calabi-Yaus. Okay. Maybe let's do the let's fix phi to be 1 plus minus delta. This thing. So when I do phi restricted to a fiber, so let's assume that the fibers are divisors. So I'm running out of time, so let's assume the fibers are divisors. Then if I restrict phi to this thing, I get something which is numerically equivalent to delta. And so I know that F, this is a Calabi-Yau there. Okay? And now there's extremely strong result in Hegon-McKernan-Schur, which says that basically the singularities of Calabi-Yau pair are like somehow finite. And so they say that if delta is very, very small, then this pair is KLT. Okay? So this is a super strong result which I want to advertise. Is that if I have such a divisor, which is basically not far away from delta, okay, then I can and everything is Calabi-Yau, then this pair is KLT. Okay, and this is like, it's a very strong result. This is lemma 6.1 in Hegon-McKernan-Schur. Like the right has a lemma, seems to be not the most important result, but it's a key result in their paper. So this implies that this is KLT. So now if I go back to my Mori fiber space, I know that this new pair X sigma is KLT over the generic point of the fiber, of the base. Now I can use Ambrose result. And so here I really need Ambrose canonical bundle formula, that he asks only that the fibers are KLT, like the general fiber is KLT. So I can still use Ambrose result even though X sigma is not KLT. And so this is a key point of the argument. And so Ambrose canonical bundle formula implies that Y, delta Y, is a Calabi-Yau pair. Okay? Like here, this is a Calabi-Yau pair. So now if you go back to the argument, I'm allowed to slice here by a general member. And so a general member here is going to be of general type. Okay? Because I'm slicing, so I'm taking a general member in F upper star H, which is a semi-ample divisor. So the generic member is of general type, which contradicts this fact. It cannot be a Calabi-Yau pair. Okay? So the volume cannot be arbitrarily large. Otherwise I would get a Calabi-Yau pair downstairs. And so here you have boundedness. So you combine all together and you get boundedness of these guys. And then, like, I didn't finish the proof, but it's okay. So I was assuming that there is a very ample divisor with bounded degree here. And so you can get that in low dimension using BAB. Or if the fibers are one dimensional, I can use effective semi-ampleness for the canonical, for the moduli part of the canonical bundle formula. And so Y would be again a Calabi-Yau with DCC coefficient, and then I can run induction. And so that's why I have the restriction on the dimension, because either I have to use BAB conjecture or I have to use the semi-ampleness, effective semi-ampleness for the canonical, for the moduli part, which we know only if the fibers have dimension 1. Okay, sorry for being a little bit late. Thank you.
Can you say again why you don't need to worry about the size of the coefficients? So those a while ago.
So the coefficients are fine because I'm always looking at 1 plus delta, right? Basically, these have coefficient like half. I can choose them. And here I know that these are in a DCC set.
Okay.
And so they are uniformly bound. So the trick is, again, I'm using 1 plus delta.
Okay.
So delta can be arbitrarily small, but it doesn't have to be DCC. Because in the theorem that Hegel mechanics should prove, they don't need that. Okay.